Lecture 8, Module 2, DMAIC Improve Stage 1. Select Solutions, Monte Carlo Simulations. In this module, we'll be looking solely at the Monte Carlo simulation, a very, very cool tool and very easy to use in Minitab. Monte Carlo simulation. This is used as a problem-solving technique to approximate the probability of certain outcomes by running multiple trial runs called simulations using variables that are demonstrating some random behavior. Monte Carlo analysis relies on random number generators to create variable process input data that we can then analyze for their effect on the process outputs. The objective of the Monte Carlo simulation is to understand the range of possible outcomes for the outputs by mathematically manipulating the potential inputs. Now here we see a nice diagram courtesy of Mr. Adams from his article, Design for Six Sigma, a Potent Supplement to Quality by Design in Pharmaceutical Manufacturing magazine. On the left we see inputs X1, X2, and X3 going into a process, and then two Y outputs on the right. And we see the X1 input, the variability of that input is following a normal distribution. X2 is following, looks like an exponential distribution, and then X3, input 3, is following a uniform distribution. And on the right, we see two outputs. Y seems to be following a normal distribution, and then the Y2 is following, looks like maybe a Y-ball distribution or something like that. And we see some failures there. So we don't have perfect performance for a Y2 in this scenario. Well, the Monte Carlo simulation allows us to look at the Taguchi ideas of parameter design. For instance, we can examine the process to see if we can improve it by shifting the means of the variables. So what if we move the mean of X1 over here and shifted the mean of X2 over here? What would be the effect on the process? Would that improve the process? Would that get us a better output? And we can do this simply mathematically. So let's create a column of random data as we wanted with a normal distribution. So we select Calc and then select random data and then select normal. It's that simple. And we'll get this dialog box. So we'll be able to create a column of 1,000 rows of random RPM data with a mean of 2.0 and a standard deviation of 0.1. And we'll put them in this column here under RPM. So here's our column RPM. We're going to store our data in an RPM column. We're going to make 1,000 rows. And the mean is going to be 2 and the standard deviation 0.1. We click OK. And bingo. Minitab creates a column containing 1,000 random RPM data with a mean of 2 and a standard deviation of 0.1. So there we see in the first row the RPM is 1.94924. Next, we'll create a column of 1,000 rows of random batch size data with a mean of 3.0 and a standard deviation of 0.1. So batch size goes into where we store 1,000 again, and with a mean and of 3 and a standard deviation 0.1. And again, we get batch size data here, 3.2. Then we'll create a column of random time data with a mean of 5 and a standard deviation of 0.1 the same way. Now, after we're done with that, we run the DOE, scroll through the session window and find the transfer function. What's the transfer function, you say? Well, remember the slope of the line equation, y equals ax plus b, and the equation y equals ax plus b defines the response of y based on changes in the variable x input and its y-intercept. As we saw before, Minitab changes this to be y equals b plus ax instead of y equals ax plus b. And in DOE, there's more than one variable. So for a design with 3 variables, like the equation we saw before, you have y equals ax plus 1, ax2 plus ax3 plus the interaction of 1, 2, 1, 3, 2, 3, and 1, 2, 3 plus the intercept. And again, that's our transfer function. However, Minitab will express it as y equal at the bottom, all the way at the bottom, as y equals b sub 0 plus ax1, ax2, ax3 plus ax1 times 2, ax1 times 3, ax2 times 3, and ax1 times 2 times 3. Or as Minitab puts it, it uses b's. Now, open the calculator again and create the transfer function in the expression text box. Store the data in a column that we create called %RSD. So we'll click on %RSD, and that's where we'll store the data. And then we'll type in the coefficients that we find in the transfer function into our calculator. And we'll use it's recommended to use the calculator itself to enter your data, and also to use the function keys. Now, you can type in the numbers, so 15.5632, which is equal to the y-intercept. If you look at the transfer function again, you'll see constant is equal to 15.562. That's the y-intercept. Plus 4.92338 times RPM. If you look back at the session window, you'll see the RPM coefficient is 4.92338. So we want to multiply that coefficient times our RPM. And the easiest way to do this is to use the keypad to click in the 4.9328, click on the multiplication sign, and then go over to the column, the select column in the calculator, and just double click on RPM. That will automatically bring it into the field. Don't type it in. You can make mistakes, and Minitab will get confused. The easiest way is to use the calculator's keys themselves. Click OK, and it will create the data based on the input data that we have already entered randomly. So boom, the column of data calculated from the transfer function based on the Monte Carlo simulations of the batch parameters is put into the column. As we can see in row 1, with an RPM of 1.94924, a batch size of 3.23924, and a time of 4.94875, we'll have a %RSD of 2.97797. If we go to the next row, there's a little bit of a deviation in each one of these parameters, and it affects the %RSD. In fact, in the second row, quite a lot. Now let's perform a process capability analysis of this simulated data. We have 1,000 data points here that are simulated data of a batch result, output result, based on variation in these parameters. So we'll look for the data in %RSD. We set it a subgroup size of 1 individuals. And since this is going to be content uniformity data that we're looking at, we will use an upper spec of 6, or whatever specification you happen to be dealing with when you run your simulation. And here's our process capability generated. We see here's our 6% RSD. And our process capability is 2.34. CPK also of 2.34, which is very good. But can we improve this? So let's design our parameters. Let's move the mean of the batch size data a little bit higher, and we'll create a new column of batch size data. Now, here's another thing. After you've created the new values, you must recalculate the %RSD. Minitab is not like Excel; it will not automatically update the results of every cell. So go back into the calculator, reopen the calculator. Fortunately, the transfer function will still be there, and just click OK. It will recalculate the %RSD column, or whichever column you have happened to select. So now with the new data, we again compare it to the 6% RSD, and we see, CPU of upper of 3.72 and a CPK of 3.72. Definite improvement in the process capability. So within a few clicks, we can determine which direction we need to go in with that one parameter. If we increase that parameter, we will get much better results. Now, another thing to look at is what's called tolerance allocation, or as I said before, tolerance design from Taguchi. What if we were to tighten up the variability of each one of these inputs, make them better? So we can actually look at that. With that, if we tighten up the deviation of each variable, will we tighten up the variability of our output? Well, we can do the same thing. Tolerance allocation will tighten the standard deviation of data for time, for instance. And we'll create a new column with time data. So the time is still 5, but instead of 0.1, we'll go to 0.05. So we'll really tighten up on the time data. We generate new data. And what did we get? Actually, we didn't do much at all. So no real improvement in process capability. Moral of the story, simply tightening specifications is not always the best way to improve a process. Getting on the right target is. Improving all the different inputs is. Tightening specifications also can be very costly, because if you tell your suppliers that they need to be much tighter in their specifications, that will come at a very high cost. So be sure you know what you're doing before you ask your suppliers to do that. Monte Carlo simulations can be used to explore the design space found in a DOE, and really can effectively look for opportunities for process improvement from the convenience of your office, without the expense of raw materials or interfering with the manufacturing schedule or spending time on weekends or whatever it may be. And it can be done within minutes using statistical software such as Minitab. Very, very, very powerful and valuable tool.